Hello everyone. In today's lesson, we're going to begin covering hypothesis tests. The main purpose of statistics is to take data from our sample and then try to make some inferences about our entire population. There are two main approaches that we can consider. The first is we can estimate a population parameter that we're interested in. This would be things like using point estimates like x bar in order to estimate what mu is, or confidence intervals in order to figure out some interval that we are somewhat positive or confident that the true value falls within the parameter. The second method is we can test the hypothesis about the values of those population parameters. So while confidence intervals allowed us to find ranges of reasonable values for the parameters, we're more interested in this case in letting us make decisions about specific values of those parameters or relationships between parameters. Specifically for this course, we generally are going to be focusing on two main types of hypothesis tests. We're going to begin with hypothesis tests for the population mean mu, and then we can also do hypothesis tests on how to find the proportion p. So let's first start with what is a hypothesis. Well, there's two hypotheses that we're actually going to need to do a hypothesis test. The first is called the null hypothesis, which is written as H0 or H0. And this is going to be our initial claim. The object of our hypothesis test is then to take this initial claim and test whether it appears to be true. So for the time being, what we're going to do is any claim that we make in the null hypothesis, we're going to treat as a true statement. And then we're kind of going off the, if this were true, does it make sense based on our data, or does it seem to point in some other direction? This other direction is going to be our alternate hypothesis. So this is written as either H1 or HA for alternate hypothesis. This is what we as researchers actually believe is true. We want to show that the evidence points towards this alternate hypothesis and refutes the null hypothesis, which then leads us to have two possibilities for this hypothesis test. We can either reject the null hypothesis, or we can fail to reject the null hypothesis. We don't ever actually say that we've proven or shown that our alternate hypothesis is true. So generally, when you're finding out what hypotheses to use, you're going to start with this alternate hypothesis, the claim that you believe is true. The null hypothesis is generally going to be some known statement, some accepted claim, or it's going to be, well, whatever would refute our alternate claim, which we believe is true. So in this, we actually want to show that the evidence actually shows that this initial claim is not true in order to strengthen the case that our alternate hypothesis is in fact true. Now for this course, because this is an introductory statistics course, our null hypothesis will always include the equality. So you may see this written in two ways. In this class, I generally am just going to write our null hypothesis in the form mu is equal to some value. But for example, if you're using certain books or tools, for example, like Pearson's MyLab, you would actually possibly have this be less than or equal to or greater than or equal to some value. Now, can you do hypothesis tests without that equality in the null hypothesis? Yes, you can. But it actually is very complicated, and it kind of goes beyond the scope of what this course in particular is looking at. So I'll actually look at that later when I'm doing mathematical statistics, and anyone who takes that course, in order to look at how you would calculate a null hypothesis that is not including the equality. And this becomes a lot more complicated because now you have to consider a lot more conditions. So let's talk a little bit more about this alternate hypothesis. When we are testing some null hypothesis, we have to test it against something, otherwise it's not clear what rejecting or failing to reject our null hypothesis means. And this is actually why it's so important to look at what is the claim that we believe is true, our alternate hypothesis, because what that's going to do is that's going to give us the alternate conclusion based on whether we reject or fail to reject our null hypothesis. So this alternate hypothesis is actually set to follow the aims of our research goal. Now again, we do not ever say that we accept or prove our alternate hypothesis. And this is because, as statisticians, we tend to be very conservative. There's always that possibility that either we just have made an error or that there's bias. So even if we did everything correctly, this can still end up being incorrect. So in this case, we never say accept, we never say prove. What we do is we have enough evidence to reject the null hypothesis, strengthening our case, or we don't have enough evidence to reject it, meaning we failed to reject the null hypothesis, which means that we don't have enough evidence to say that our alternate seems to be true. Another reason that we focus on saying, do we have enough evidence to reject or fail to reject the null hypothesis, is because one of the key aspects of hypothesis testing is that it relies on this level of significance. So if we were to change this level of significance, we actually could change our conclusion based on whatever level of significance we selected. Now, as statisticians, we should always be choosing this level of significance before we do a hypothesis test. There are some places where what people do is they will just run a hypothesis test without this level of significance and see at what level of significance you would have enough evidence to reject the null hypothesis. In fact, if you ever do any sort of modeling or anything like that in R, it will tell you the significance level, for example, of different variables or whatever you're doing, without you even giving it a specific level of significance. But we're going to come into this approaching it with the mindset of, I'm going to see if my evidence points one way or the other based on some certain conditions like the level of significance. And this will allow us to make our decision. So in short, to begin doing your hypothesis test, you need to first start with your initial claim. Now, a lot of times when we're doing problems for this is going to be a claim from some outside source. This could, for example, be some information from a vendor, from prior studies, or it even could just be something that refutes what you believe is true. And this is what you're testing your claim against. Your alternate hypothesis is the goals of what you actually believe is true as the researcher. There's no unique way that you have to write your null and your alternate hypothesis, but there are some main ones that we're going to use, and most people do as well. So let's look at the framework for how we actually set up our null and our alternate hypothesis. Now again, for this class, we're always going to have our null hypothesis in the form of our parameter, let's call it mu in this case, is going to be equal to some value. I'll call this value A. It could be some number, 65.5, something like that. And then our alternate hypothesis from there will either be mu is not equal to A, we could have mu is less than A, or we could have mu is greater than A. Now, again, the null hypothesis must always include the equality for the type of hypothesis test that we're doing. So this also could be structured a different way, which is you may actually have a different null hypothesis based on your alternate hypothesis. So in this case, for example, if I wanted to test mu is not equal to A, then my null hypothesis would be that mu is in fact equal to A. It's sort of the complement of what we're actually trying to prove. If I have an alternate hypothesis that is mu is less than A, then the complement of this would be, for the null, mu is greater than or equal to A. And then finally, if I have, for my alternate hypothesis, that mu is greater than A, then the complement would be mu is less than or equal to A. And notice in all of these, they do include the equality. And these statements are basically equivalent to each other. And the reason is, and you'll see whenever we start doing these calculations, is that once you have that equality, this is sort of the opposite of what we're saying. So for example, if I said that I believe that mu is less than A, well then by showing that mu is, in fact, we don't have evidence to say that it's less than A, we're kind of showing that it either is equal to or it's greater than or equal to. We're kind of showing the same sort of thing. This is true also whenever we're doing any other parameter. For example, if this was proportion P, it would be the same idea. You could either set it up as the null hypothesis, P is equal to some proportion, 0.6 let's say, and my alternate hypothesis could be that P is not equal to 0.6, P is less than 0.6, or P is greater than 0.6. Or I could do it in this form. P is equal to 0.6, alternate hypothesis, P is not equal to 0.6. P is greater than or equal to 0.6, alternate hypothesis, P is less than 0.6, and so on. Now, unlike when we did confidence intervals, we actually do have to consider what type of hypothesis test we're doing when we're looking at a single parameter, in this case, mu. So the first thing we have to do is we have to look at the fact of whether we are doing what's called a one-tail or a two-tail test. So when we start with our alternate hypothesis, we need to look at, is it one tail or is it two-tail? And this is going to be determined by how can we reject our null hypothesis. If it's one tail, then we have to consider the direction. For example, if I'm doing my alternate hypothesis where the direction I'm interested in is less than, then this would be a left tail test. If I'm doing my alternate hypothesis mu is greater than some value, this would be a right tail test. And then if we're doing a two-tail test, this is just called a two-tail test. This just means that I could reject it in either direction. If my data is very far above or below what we would expect based on our null hypothesis, then we can reject it, either far below or far above. Now, how do you know which test you're doing? Well, when you have a word problem, this is generally going to be based on the language. For example, if we're trying to show that something is different than, or not equal to, or we want to just show that we reject the claim, but we don't give you a sense of direction, these would be indications that you're doing a two-tail test. If we believe that our value is greater than, or we want to show that it's more than, or we want to show that it's higher than this value, that would imply we have a right tail test. Similarly, if we want to say that it's less than, smaller than, fewer than, these would be words that indicate we're doing a left tail test. Here we can find two examples of setting up your null and your alternate hypothesis for a hypothesis test. The first example says an SAT tutoring center claims that the average math scores of their students in the SAT is 500. That's their initial claim. That's what the company is claiming. Consider a small sample of 20 students. The sample mean of their scores is 521.5. Previous records show that the standard deviation is 120.5. At the 5% level of significance, do we have sufficient evidence to prove that the average math score on the SAT are different than 500? So notice we had that word different. We want to see if it is different. That's what we're trying to show. So in this case, we're going to start with our alternate hypothesis, which is going to be that it's not 500. This means that I could prove this or show this by having a value that is far above, meaning that this value might be too low, or far below, meaning that it might be too high. And then I'm going to write my null hypothesis, which is that initial claim the company made, which is what I'm trying to refute, which is that mu is in fact equal to 500. Now, because this is a not equals to statement for our alternate hypothesis, this means what we would be doing is a two-tail hypothesis test. The second example says an SAT tutoring center claims that the average math scores of their students on the SAT is 500. Consider a small sample of 20 students. The sample mean of their scores is 480 with a standard deviation of 120.5. At the 5% level of significance, do you have sufficient evidence to prove that the average math score in the SAT are less than 500? So now the claim that we're trying to actually test is that the scores are less than 500. So our alternate hypothesis is mu is less than 500. This means that our null hypothesis will be mu is greater than or equal to 500. Or again, if you wanted to, you could just write this equal to. It works out the exact same way. Now, before we get into calculation and also where this can go wrong, let's quickly talk about the steps that you'll take when doing a hypothesis test. So the first is you want to identify your parameter of interest. Again, for this section, we're going to be focusing on the mean mu, but this could be standard deviation, sigma. It could be variance, sigma squared. Any parameter that you're interested in or the difference of parameters, this would be what you're actually doing the hypothesis test on. Then, if needed, we need to check our assumptions. So this would be, for example, are we able to use the standard normal distribution, or do we have to use a student's t-distribution? The next thing is to write our null hypothesis, that initial claim. And then we want to identify our alternate hypothesis and then what type of test we're doing based on that alternate hypothesis that we have selected. Then we want to check the requested level of significance. This should be given in the problem. If it's not, then our default is alpha equals 0.05. The three most common used alpha levels are alpha equals 0.1, alpha equals 0.05, and alpha equals 0.01. Though again, the default is alpha equals 0.05. So if someone just says test the claim, but they don't give you a level of significance, you would know that you are using alpha equals 0.05. In fact, if you do this on any sort of program, R, Python, Excel, this will be your default unless you specify otherwise. Now, once we have this level of significance, then we need to figure out the appropriate test statistic. This is going to be based on those assumptions that we need to check. So we're going to check our assumptions to see what distribution would describe our data and allow us to do our hypothesis test. Once we've done that, we need to test what's called the test statistic, which will go into all of this, how you calculate this later in the lessons. Once we've tested this test statistic, we could actually be done with our hypothesis test if we wanted to by using what's called the critical region method. But generally what we're going to do is we're going to take it a step further, and then we're going to calculate our p-value to then give us an indication of not only whether we reject or fail to reject the null hypothesis, but how strong the evidence is in favor or against our alternate hypothesis. Once you've done that, you then need to make a conclusion based on these previous steps we've taken, and then we want to state our conclusion. Now, we usually are going to use the form at the blank level of significance, we have sufficient or insufficient evidence to reject the null hypothesis. Or you could write it in some form like that. At the blank level of significance, we reject the null hypothesis, or we fail to reject the null hypothesis, something like that. What is the hypothesis test actually telling us? In this slide, you can kind of see an example of what this process would look like. So step one, we're going to check the details and see if the question is about a one sample test for mean or one sample test for proportion. Then, once we have that parameter we're interested in, we're going to state the appropriate null hypothesis, our H0. We're going to state our alternate hypothesis, H1 or HA, and then that's going to tell us the direction or type of test we're doing, left tail, right tail, or two tail. From there, we're going to check our assumptions. Now, we'll talk more about assumptions when we actually start doing this, but generally what we're going to be focusing on is, can we use a normal distribution? And we're going to be using our central limit theorem to look at, do we have a known normal distribution, which in this case we'll use the fact that is sigma known. And then our other check that we're going to do is, do we have a large enough sample size to assume that it's a normally distributed data? So for this class, we said that value is n greater than or equal to 30. Now, as a reminder, when we have a problem like this, we will have ways of determining whether sigma is known based on the context of the problem. If sigma is unknown, we're assuming that our data, though, does have a general bell-shaped symmetric curve, so therefore we only need n greater than or equal to 30 to show that we have enough data to assume that it follows a standard normal distribution. Is this always true? No. In fact, if you're using real data where it's not so clean cut, you actually may need a larger sample size than this to be confident in your hypothesis test. And this is sort of just a rule of thumb, and most books will use n greater than or equal to 30. If we were doing proportion, we would need to instead look at, do we have enough data? In this form, it would be that NP is greater than or equal to 5, and NQ is greater than or equal to 5. Now, one thing I want to point out about this part real quick is that this first set of assumptions for mean, mu, is an OR statement. If sigma is known, use standard normal. If n is greater than or equal to 30, use standard normal. If both are true, use standard normal. That's Z distribution. If both fail, this is when we would use the student's T distribution. For proportion P, this is an AND statement. It means that both must be true. In order to do this hypothesis test, because we're going to be using a normal approximation basically, we need to have enough data to show that NP is greater than or equal to 5, and also at the same time, NQ is greater than or equal to 5. If one of these fail or both of them fail, you would have to use some other method to do your hypothesis test. But for now, we're going to be focusing purely on the mean mu. From there, we now know which distribution we're looking at. So based on that distribution, we can find our critical value, which will tell us where our rejection region is. This will tell us if, based on when we do our test statistic, does it fall in the rejection region or does it fall in the fail to reject region? Our test statistic for mu is just going to be, if we're using the standard normal, Z is going to be equal to x bar minus mu over sigma divided by square root of n. And if we're using the student's T distribution, this is of course going to be based on our nu, or number of degrees of freedom, which is going to be n minus 1. This is going to be equal to x bar minus mu over s divided by square root of n. For our proportion, we would need to use z equals p hat minus p divided by the square root of p times q over n. Now remember, this only works if both of these are true. We don't really have an alternate that we're going to cover right now of what we would do if this fails. Once we've found this test statistic, we can actually look at, do we reject or fail to reject our null hypothesis? But we're actually going to take a step further, and we're going to then calculate our p-value, which we'll talk more about that when we get there. Then from that, we'll conclude our hypothesis test, and we'll figure out whether we reject or fail to reject the null hypothesis, and what our conclusion is, and state that. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.